Bismillahirrahmanirrahim. This is the lecture number 2 and 3 for those students who didn't attend the lecture, or especially the section A, who didn't have any class of the engineering dynamics. And this will complete the basic concepts and whatever we have discussed in chapter 1 and in the beginning of the chapter 2. So I hope now all the students are at the same length, at the same pace. And I have also put lecture number 4 and 5, which completes the rectilinear motion, the Cartesian coordinates. Any question, any suggestions, any queries, please put on the WhatsApp engineering dynamics workgroup. Scalar quantities, I think you have studied from the basic classes. Scalar quantities are those which can be represented by the magnitude and the proper unit. You know that it's a length, mass, time, distance, volume, density, temperature, speed. These quantities does not need any direction. So therefore these are called scalar quantities. They can be added, subtracted, multiplied, divided. Any mathematical function is being provided, being done similarly as we have done on the numerics. So it's very simple. Now the other important parameters, important quantities which have some challenging aspects is the vector quantities. And those quantities basically which needs magnitude, of course proper unit, and a specific direction is required are called vector quantities. For example, velocity, acceleration, force, weight, torque, momentum. Acceleration is the increasing or decreasing, force is push or pull, weight is the downward direction, torque clockwise, anti-clockwise, I, J, K components in the 3 dimension. Momentum, of course, mass is a scalar quantity and velocity is a vector quantity, and of course momentum will be in the direction of the velocity. What is a unit vector? Basically, unit vector is a vector whose magnitude is 1. Why we use unit vector? Because if you want to represent a magnitude, a quantity which is a vector quantity, when we represent it in the form of vectors, so first we find the unit vector and then we multiply that quantity with this unit vector, such that this unit vector will not affect the magnitude of that quantity, but it will give the magnitude of different components in x, y and z, I, j and k. Equal vectors, the vector which are parallel to each other and have the same direction and equal magnitude. Remember that they are parallel, of course, in the same direction, and equal magnitude are called equal vectors. Like vectors, the vectors which are parallel to each other and have same sense but unequal magnitude are known as like vectors, right? So for example, you have a vector I plus j plus k, I plus j plus k, and other vector is 2i plus 2j plus 2k. These are the two same vectors. Just one vector is multiplied, the second vector is multiplied with a magnitude of 2, or the first vector is being divided with the magnitude of 2. So these vectors are parallel to each other and maybe they have unequal magnitude but in the same direction. Let's see, the vector quantities are being represented by an arrow, and this arrow is plotted to some scale. You see there's a vector PQ, right? This is the tail and this is the head, and this arrow is showing the direction. There's another vector RS at some angle from the horizontal, and this is the tail and this is the head. If I want to add these two vectors or any two vectors, so basically we use the head to tail rule. Head to tail rule means the tail of this next vector, which is a preceding vector, coincide with the head of the preceding vector, which is the previous vector. And this pink color vector is basically a resultant, with tail coincide with tail and head coincide with the head. Now, what is the subtraction of a vector? Basically, subtraction of a vector is again an addition of a vector. The only thing is that, for example, in this case, if we are subtracting the two vectors, let's see this one, this is BC. So what we did, basically we are doing A plus minus B. So first of all, we draw the negative of a vector, this BC, negative of a vector. This negative vector is equal in magnitude of BC but in opposite direction. So let's see, we plot the same vector but just in the opposite direction, equal in length of the given vector BC but only in the opposite direction. Again, it is being added head to tail rule, right? And this is the resultant pink color AC. It is basically, I can say it's AB minus BC. It's basically AB plus of the minus BC negative of a vector of BC. So negative of a vector or subtraction of a vector is simply addition, but only we take the negative of that vector which is being subtracted. I hope this is being clear. Addition of vectors, again I told you the rule is only one, that is head to tail rule. The tail of the preceding vector coincide with the head of the preceding vector, and in the resultant head and tail coincide with each other. The methods used for the addition of vector, please remember that the rule is head to tail rule. The method is, maybe you can use graphical method, you can use parallelogram method, or you can use rectangular component method. In a graphical method, what we did, first of all we use a proper scale, right? And then we draw each vector one by one. For example, if you see this vector has a magnitude of 3, whatever, this vector has a magnitude of 6, this vector has a magnitude of 5. First vector is a magnitude of 3, making an angle of 45 degree. So we will make the reference here, right? We make the reference here, right, and draw an angle of 45 degree first of all, and then for example I assume magnitude 1 is equal to 1 centimeter, then draw a line of 3 centimeter. You can take any scale, but the scale should not be very large, should not be very small. It should be proper such that it will fit into your paper or your space, right? Then the next vector is a 90 degree. I draw the reference and then draw an angle of 90 degree and with the length of 6 centimeter. Then again draw the reference and then make an angle of 150 degree, please, from right positive x-axis, anti-clockwise angle is positive, and then we draw a length of 5. That's all. So this is the starting point, this is the ending point. I join them. This is blue line is my resultant. I measure this becomes 11 centimeter. So 11 multiplied by my scale is 1, so therefore it's 11. And then with the reference here, I measure the angle from this reference, please, this positive x-axis. I measure the reference, which is basically comes to be 102 degree. So the resultant of these three vectors, which are given at certain orientations, orientation means angle, it is at the about 11 meters or 11 millimeter per second, whatever, at an angle of 102 degree from the positive x-axis. So this graphical method has certain advantage. This will give you a pictorial representation how the vectors look like and how they follow the path. But of course, it requires a lot of accuracy when you are making you're making these vectors. Of course, it is not as accurate as the mathematical methods, the geometrical methods, but it will give the idea and how the polygon should look like and give you an approximate result. The other way that we have to take the rectangular components method. Why they are called rectangular components? Because these two components had an angle of 90 degree with each other. For example, if I have vector S, which is making an angle theta with the x-axis, right? So if I put the light from this top, the image of this S on the surface is this. I say this is x component because I say horizontal axis is x. Similarly, if I put the light from this vertical and for example, if we have a vertical screen, we get this image, right? This is basically the y component of this vector S. Now, if I need to find the magnitude in terms of some mathematical relationships, so you know that I use the trigonometric relations. So if I say cos of theta is equal to base upon hypotenuse, cos of theta is x by s. To angle 90 to opposite is basically hypotenuse, and adjacent line adjacent side is base. So S is equal to x cos theta. X is equal to S cos theta. Similarly, if you take sine, it's perpendicular upon hypotenuse. So therefore we get y is equal to S sine theta. Remember that any component opposite to theta, whether it is the x-axis or the y-axis, is always sine theta, and adjacent is always the cos theta. Now this is a right angle triangle. If I need to find the magnitude from these, so S square is equal to hypotenuse square is equal to perpendicular square plus base square by using the Pythagoras theorem. And then I can find the magnitude. S is equal to under root of x square plus y square, that you know that. The finally is the angle. You can find the angle of this resultant by using tangent theta is equal to perpendicular upon base, tan theta is equal to y by x, theta is equal to tan inverse y by x. So if you need to find the resultant of two or more than two vectors, n vectors, the steps are here. Find all x and y components of the vector first, then add all the x component of the vectors and find the resultant vector x, then sum all the y components of the vector and find the resultant vector ry. Using the Pythagoras theorem, the r is equal to rx square plus ry square. And finally the angle, the tan theta is equal to ry by rx from the positive x-axis. Of course, the value of angle of positive x-axis is taking counterclockwise positive. You will see whether the ry and rx is positive or negative. Depending upon the coordinates, you can find the angle. If both of them are positive, of course, angle lies in the first quadrant. If the ry is positive and rx negative, you are in the second quadrant, then your angle will be 180 minus theta. If both of them are negative, then you are in third quadrant, your angle will be 180 plus theta. And if ry is positive, ry is negative and rx is positive, you are in the fourth quadrant. In that case, your angle, positive anticlockwise angle, is 2 pi or 360 minus of theta. If you still have any questions regarding this, please let me know. Now, next thing is when you are multiplying two vectors, we talk of addition of vector, we talk of the subtraction of vector. So now scalar product or dot product. When two vector quantities are multiplied, the resultant is a scalar quantity. This is called scalar product or dot product or inner product. Scalar or dot product, we define A dot B vectors. A magnitude of A into magnitude of B into cos of theta, AB cos of theta. Remember that if this is a vector A and this is a vector B, we take the angle between the vectors, not from the x-axis, please. It is the angle between the vector. Scalar product is the magnitude of a multiplied by the projection of B. If I say A dot B, it means the projection of B along A. Right? Obviously, if A is perpendicular to B, of course, if A is perpendicular to B, then of course there is no projection of B along A, therefore dot product is 0. If you find the projection of A along the A, simple A dot A is A square sine of theta A square, right? Hence A is equal to under root of A minus A, which is the magnitude of A, right? So A dot B is equal to AB cos of theta. The properties of scalar products, of course, I dot I, J dot J, K dot K is equal to 0 because cos of 0 is 1 and all other I dot J, J dot K or K dot I, they are perpendicular to each other. Therefore, cos of 90 is 0. So the result is 0. Now, if for example, A dot B, we are given the position vectors in terms of Ij and K, Ax of I plus Ayj plus Azk, Bx of I plus Byj plus Bzk. We just multiplied I with I, J with J and K with K because Ax into Bx, I dot I is equal to 1. Ay into By, J dot J is equal to 0. Az into Bz, K dot K is equal to, K dot K is equal to 1 and J dot J. All other I dot J or I dot K or J dot K or J dot I, they are perpendicular, so dot product is 0. And the other property is very important, that A dot B is equal to B dot A is a commutative property. If you multiply you take the dot product, either A dot B or B dot A, it remains same, it gives the scalar value. Similarly, if you take the distributive property A dot B plus C to A dot B plus A dot C, either you add these two vectors, then take the dot product, or take the dot product individually and then add, you get the same, as this property holds for the other numeric numbers also. For example, if C is equal to A plus B, if I need to find C square, so I take the dot product on both sides, C dot C is equal to A plus B and A plus B. So please, C square is equal to, it multiply A square, right? Then A B into B A into B dot B, which is A square plus B square plus 2A dot B, which can be written as A square plus B square plus 2AB cos of theta AB. If the angle between them is 90 degrees, then this term goes to 0. Then A square plus B square is equal to A square plus B square, right? And if the angle is 0, it becomes A square plus B square plus 2AB. Here parentheses are important. Note, if U dot V into W is not equal to U into V dot W, because one vector is a vector along W, U dot V is along W, the other is along the U, because V dot U. So here the order in this case means if you're taking the product, then of course the order is important. U dot V in the bracket multiply by your dot product with W is not equal to U into V dot W, because you take U dot W is in the W direction. If you take this one, V dot W is U. So these are the different. So in product it does not hold the associative property. Vector product or cross product or outer product. So when two quantities are multiplied and the resultant is again a vector quantity, this is called a vector product. Vector or cross product of two vectors we can define as A cross B, because we are using cross, therefore it's called cross product. Or why it is called vector? Because eventually after multiplication it's always again give you the vector quantity. Magnitude of A, magnitude of B, sine of theta, n hat. N hat basically is a unit vector in the direction of the A cross B vector. Again, if we have two vectors A, B, if I take A cross B, it means it is coming out of the screen, right? So if I use the right hand rule, the curl of my finger is showing the direction of the product, and of course the thumb is moving out of the paper, or in the case of out of the screen, and that is the value of A cross B, right? So the direction of this one is this. You can also show it by this. So A cross B, I think the right hand rule is simple. Use this rule. Properties, of course, A plus B cross C is equal to A cross C plus B cross C. This distributive property it holds the distributive property. But A cross B is equal to minus B cross A. So commutative property does not hold. Of course, A cross B and B cross A are equal in magnitude. But if A cross B is in this case, in our the figure shown here, if I say from A to B, it is out of the board, and B cross A is into the screen or into the board. So therefore, direction is opposite. Similarly, associative property does not hold. Okay, if M is any scalar quantity, if M A cross B, this you can multiply M with any one of the vector, right? And then take the cross product, or you take the cross product and then multiply by M, or initially multiply A cross B and then multiply with a scalar quantity like 2, 3, 5. It does not important. They are same. Importantly, A cross B is equal to 0 if vectors are of course parallel, because sine of 0 is 0. So the cross product is maximum when angle is 90, and cross product is minimum when angle is 0. Dot product is maximum when angle is 0, and cross product is maximum when angle is 90. The practical application of the dot product is one of the very simple examples. Most is told the work is a dot product of force and displacement. Force is a vector quantity, and of course displacement is a vector quantity, but the work is a scalar quantity. Similarly, voltage is E dot D. E is electric intensity and D is the displacement. Both of them are vector quantities, but voltage itself is a scalar quantity. Similarly, in the case of vector product, torque is a cross product of arm of force into force, R cross F. Please, r cross f and f cross r are not same because both of them are in opposite direction. So in the case of cross product, you have to have taken care of the direction r cross f. So r is a vector quantity, force is a vector quantity, but we need torque will have a certain direction. If you talk of in 2D, of course it is in k direction, or clockwise or anti-clockwise. If it is in 3-dimensional, of course it has certain components in I, j and k. So these are basically the vector product. So if I show you the Cartesian coordinate system, the vector product, for example, we have a x, y and x, y and z. Of course, we mostly show the unit vector along the x direction is I, unit vector along the j is, of course, along the y is j and along the z is k. So I cross I, of course, 0, j cross j is 0, and of course k cross k is 0 because the angle is 0. Remember that if I move, if I say I cross j, if I say I cross j, the net, this should be in third direction, that is k, and this direction is same in the direction, in the same direction. If I'm moving in the anti-clockwise, k is also in anti-clockwise, right? Then you say you took j cross k, again it is in the same direction, is I. Then I take k cross I, again in the same direction, that is j. But if I say j cross I, it minus k. If I take k cross j, it is minus I, and I cross k is equal to minus j. As I told you earlier, a cross b is equal to minus b cross a, right? So in the opposite direction, it will be minus. A very useful property, a cross b, if you take this one, for example, we have two vectors ax, ay, az, and similarly bx, by, bz. If I multiply, you know that the similar vectors product is 0. So a cross b is, if I multiply ax into bx, I cross I is 0, right? So if I multiply I with k, that is basically I with k is basically in the j direction, and similarly, which I told you earlier, I cross j is k. So if you either you multiply by using this relationship, these relationships, or just make the matrix a cross b, I, j, k. Please, if a is first, then put the coefficients of a first and then b. If it is b cross a, then you have put the coefficient a and just open the matrix that you learned in the previous classes and as well as in linear algebra, and then you find the same relationship. So I prefer use this determinant method, ijk, first vector magnitude of I, j and k. And if any magnitude is, if any component is not there, for example I and k, so j is 0. For example, I is 0, then j and k will be there, whatever the component is not there, put it 0. This completes the basic introduction I have given. Please read out the conversion factors in chapter 1. Now, the kinematics. I have already told you the kinematics. The kinematics is basically the effect of forces. We see the motion of a body without the reference of the force. So we talk of the displacement, velocity and acceleration. We know that the acceleration is basically the rate of change of velocity, which is v dot, right? And acceleration can also be written as, because we know that v is equal to ds by dt. So it is basically a is equal to d2s by dt square, which is equal to s double dot. Okay, you know that I think lecture number 4 in the beginning I've told you, if I have a dv by dt, ds by dt is equal to v. Okay, so from here, from a equation I find a dt, from the v equation I also find a dt, and by comparing this we find the next relationship b dv is equal to ads, that I have used when I solve the problems of chapter number 2 of rectilinear motion. So this can also be written as s dot, v is ds dot, is equal to s double dot ds. Now the next important thing is the graphical representation of different relationships between s and t. of course this is S and this is T, the graph between S and T. For example, this is the graph, right? If you find the slope at any point of the distance time graph, this is basically ds and this is basically dt. We get velocity. The slope at any instant on a distance time graph will always give you the velocity, right? The slope at any instant at a distance time graph will give you the velocity. Is it clear? If I need to find what is the velocity here, I just draw a tangent line and then find the change in velocity, change in distance, and change in distance per unit time will give me the velocity. So the slope of the distance time graph at a particular instant will give you the velocity. Now let's move to the velocity time graph. In the velocity time graph, if the tangent or the slope at the velocity time graph will give us, because this vertical line is dv and this is dt, so dv by dt is basically the velocity, and the area under the velocity time graph will give you the distance traveled. S is equal to vt, so area under the velocity time graph will give you the distance traveled. Next, this is the acceleration and time graph, and this acceleration time graph will show you how the distance is being traveled, and how it tells where the body is accelerating. You see, see here the acceleration is increasing up to this point, or maybe up to this point, and then this shows that how the acceleration is decreasing. The curve, if a curve is moving in the upward direction, it means the body is accelerating, velocity is increasing. When it is in the downward direction, it shows you that the velocity is decreasing, right? This is the way how you can represent the acceleration time graph, and from what is the information you gathered from these graphs. So now after this, I hope all of them are at the same length, and from the next lecture I will go to the curvilinear motion, first of all on the rectilinear coordinates, then the normal tangential coordinates, and then in the r theta coordinates, and then we go to the 3D, which is the r theta and z coordinates. So I hope you will benefit from this lecture, and please share this lecture for other students also of other universities. This is not only binded to you, because this is the knowledge I'm giving freely to all of them, that anyone want to gather this knowledge, it is helpful for us. Thank you very much.